Hello friends, welcome to my channel. We have watched the first video. Thank you for that. This is the second video of the series. We'll learn more about ECG in this video and in the upcoming videos. In the first video, we had learned about the newer way to approach the ECG. In this video, we will learn about the universally accepted uh, conventions regarding the ECG. So the first convention is the nomenclature of our P, Q, R, S and T waves. They could have been named as A, B, C and D, E waves, but by convention they are named so, and so here we'll continue using the P, Q, R, S, T nomenclature. The second convention that I would like to talk about is that whenever the wavefront of activation is traveling towards the lead or electrode recording the ECG, that activity is plotted on the ECG above the baseline, correct, and it is called as a positive deflection. And when the activity is going away from the recording electrode, it is plotted on the ECG below the baseline and it is called as a negative deflection. Again, this is accepted universally, so everybody continues with the same convention and we will also use the same. The ECG is recorded or plotted on the paper at the speed of 25 millimeters per second. That comes down to 0.25 millimeters in 1 milliseconds. So if 4 such quarter millimeters are taken together, this will form a complete millimeter, and for that to happen we'll have to take 1 plus 1 plus 1 plus 1, that is 4 milliseconds, correct. So on the ECG, on the x-axis there are markings for the millimeter and every 1 millimeter stands for 4 milliseconds. I feel that one small square, one large square, that kind of explanation is kind of more confusing and not measurement of the square, it is actually measurement of the distance in millimeters on the x-axis. So every 1 millimeter stands for 4 milliseconds. Same way 5 millimeters, that will come to 20 milliseconds. This is the x-axis of the ECG. This is the y-axis of the ECG. This is our ECG P, QRS and T wave. Now we know T wave is the plotting of the repolarization process of the ventricles. By calculating how broad the T wave is on the x-axis, those millimeters can be converted to milliseconds. Mind you, these durations would be real, absolute values of the repolarization event of the ventricles and not relative values. On the y-axis, the energy of the waveform is plotted at the scale of 1 millimeters, standing for 1 millivolt. But the values that we get on the y-axis, these are not the real absolute values. These are the perceived and relative values. We'll try to understand these in a moment. For an example, consider that P wave for a given patient is height of 10 millimeters. That stands for 10 millivolts. If that person who was in a supine position while taking the ECG now sits or maybe leans forward, the distance between his heart and the electrodes placed on the skin, that will decrease as the heart falls towards the anterior chest wall, resulting in increasing of the amplitude of the P wave, which was earlier 10 millimeters, it might go up to maybe 13 millimeters. Another example for that matter, if that same given patient develops a pericardial effusion, this is his heart and this is the pericardial sac, and now he gets a pericardial effusion, or these are the lungs, this is the heart, and there is a huge pleural effusion accumulating which will increase the impedance, and resultantly the P wave would be recorded of a lower amplitude. Point I am trying to highlight here is that the amplitudes, the heights of the waveform recorded in the millivolts, this is the perceived value of the force of the wavefront by the recording electrodes. It is same as example, there is a cup, sorry for my poor drawing. Imagine a cup filled with water, and under the sun, now this water starts to boil. We all know the boiling point of water is 100 degrees Celsius. So that does not mean that the temperature of the sun is 100 degrees Celsius. It is only the heat of the sun reaching this cup is 100 degree Celsius. We know that sun is a lot more hot than just 100 degrees Celsius. So this is the exact same thing which happens at the y-axis. It is not the recording of the actual voltages happening in the heart, but these are the voltages reaching the recording electrode which are placed on the skin of the patient. It is important to know about the x-axis values being absolute timings and the y-axis values being perceived relative values. Here we will learn more about wavefronts. It is very crucial to understand what is a wavefront to understand the generation of the ECG. So let's dive deep into the heart and go straight to the sinoatrial node, which is, we all know, the pacemaker of the heart. The cardiomyocyte, which is standing just beside the SA node, we'll call it as first cardiomyocyte. Understand the second cardiomyocyte and third cardiomyocyte. So as soon as the SA node triggers the activation for the heart, that activation will influence this first cardiomyocyte, which is sitting just beside our SA node, and it will get activated, and it will pass on the activation to the second myocyte sitting just beside it. It will then get activated and pass on the activation to the third cardiomyocyte. It is very similar to the game pass on the ball. A person gets a ball and he shifts the ball to the person standing on the right side of him, and that person subsequently passes on the ball to the third person who is standing on the right side of him. So every person getting the ball, every cardiomyocyte getting the current is equivalent to getting activated, which is equal to action potential. And the passage of the ball from one person to the other, the passage of the activation from one cardiomyocyte to other cardiomyocyte is called the wavefront of activation. In our given example, this is traveling from left to right. It is this wavefront of electrical activation of cardiac chambers that generates the voltage which causes deformations on the straight line ECG.